she was like, 0% chance anyone's going to be in that room. And look at this room. All right? Not only are we jam-packed to hear our main man, Matt Ritchey, wax philosophical about the awesome stuff they're doing at Great American, we are filled to the gills with a full room of awesome-looking attendees. All right, so we've got this session where Matt's going to go deep. He's got a lot of words in his intro for the abstract. I just didn't understand. All right, so we're not going to let me get in the way of trying to explain it. But what I can tell you from my work in insurance is that when a big storm is coming, you've got to scramble a lot of resources. You've got to get those resources so you can help people. So when a cat's coming in, we literally get trailers. You know, sometimes you might see Task Force 1 on the news, and they'll go and help someone out. Well, insurance companies have their own version of that. So these cat teams, they got to giddy up and get going there. We also have to start telling our accountants and our other leaders and executives, hey, we're going to have a bad day. And this is how bad it's going to be because this loss is tracking, and this is what we have at risk, and this is how much damage is going to come through. And the sooner we can get in front of that, the sooner we know the criticality, a lot of important decisions can be made that impact the expenses that we'll have, legal issues, like if you screw something up, you might end up getting sued. So the impact of this at any large insurance company, for one event, could be millions to, I don't know, billions, depending on what's going on there. So you didn't come here to hear me talk. You came to hear my main man, Matt Ritchey here, who's a senior data scientist at the second best insurance, I'm kidding, at Great American Insurance, come on now, just kidding. Over at Great American Insurance Company. He's been there since 2018. Before that, he was a math teacher, high school math teacher, so he's probably got some great stories. If any of you start to fall asleep, I imagine he's got some sort of classroom jujitsu he can use on you. So what I like to do before we have a speaker come in here, so let him know that he's loved. So let's give it up for Matt Ritchey, all right? All right.
He goes, no, I'm good with that.
All right, I got you. Yeah. Yeah. Oh, yeah. All right.
Oh, wow. Hold on a second. Yeah, awesome. Well, thank you. That was a great introduction. I don't know if I'll do better than that, so appreciate it though. As you said, I'm Matt Ritchey. I've been with Great American for 8 years. I was a teacher. This is my first time being in front of an audience live. I think this is being recorded. I'm not. Is this being
Thanks,
recorded?
Matt. I was supposed to. I'm failing left and right.
Right.
This is being recorded, so please keep it clean.
Not exactly sure. Where's the camera at?
Possibly that one. But
Okay, well, okay, gotcha. Okay. So this is my first time in front of a classroom in about 7.5 years. So kind of exciting. So I love teaching because one of the big things for me personally was just I like learning more than teaching, and so. But this is still a good opportunity to kind of hone my skills. So thank you for coming today. How many of you are in insurance? Besides, yeah. So we got the Great American people. So anybody else that's not Great American Insurance? That's it. Just one. Okay. So thank you for coming. I don't know why you're here, but hopefully this will be relevant. And then I did not use AI for this presentation. So now the proposal I might have used it, but yeah. So. Okay, so we have a disclosure here. Legal told me to do this. Basically, everything's my personal opinion, I guess, and there's no PI involved with that. So this is the agenda for today. We're going to talk about weather data first. Then I'm going to show you how I use weather data with computer vision models, and we'll talk about transfer learning a little bit. And then the last section will be LLM data extraction, and then I'll do a couple further extensions. So as was said, we need to figure out when a catastrophe occurs, and I'm going to be focused on hurricanes today. I thought hurricanes would be relevant at this time of year, but they have not been, which is actually really good for us, right? So this has been one of the least active years in the Atlantic. So they do have a reason for that. It's called the Maiden-Julian oscillation. So I learned about that last week. So anytime the predictions, they're expecting above average amount of hurricanes this year. They failed visually, so they have an ad hoc way to justify their predictions. So it was the Sierra sand dust came across the Atlantic and dissipated a bunch of hurricanes. So another thing to deal with. So I have not put those in my models this year. I don't know if they're even real, but that's the reason why. So some of this isn't super relevant for right now. Last year at this time, Milton was actually occurring, so I thought it might be relevant, but yeah. So we aren't talking about hurricanes, but it is actually transferable to any sort of catastrophe, whether it be tornadic activity, hail, wildfires, etc. So I know Ryan in the keynote gave you something like this for the AI landscape, and so what this presentation is going to kind of relate to is that the computer vision part is the deep learning. And let me ask you a question: how many of you, and I'm hoping it's not very many, so don't feel bad if you haven't done this. How many of you have trained a neural network using TensorFlow or Python? So I just want to see you say, okay, cool. So yeah, about a third, which is good. For those people who have, there's going to be a section, we're going to talk about that, you're going to be bored out of your mind, but everybody else, I think it's going to be super relevant and helpful. So then the LLM data extraction is generated AI, which when we think of AI, nowadays that's what people will think of. And then we're going to take some of the data that the LLM extracted and put it into a machine learning model. I'm not going to talk a lot about machine learning, but that's kind of the flow for today's talk. And I'll probably be about 30 minutes. I know I'm supposed to be about 40. And then I'll take questions. I do a lot better with questions. So I'm going to be focusing on data and modeling. I'm going to skip the data engineering. So I know you're a data engineer, right? So data engineering is super important. And then Ryan talked about that in his section, in his keynote, that they want to try to not get rid of, but just allow people to access the data by themselves and have data engineering be not as involved. But for this presentation, in order to do this, and everything I show today is open source, so I can technically show you how I do that with code. I'm not going to talk about the data engineering part because it's very complicated, so it's just heads up there. And then I always make a note when I do this internally within Great American that we're talking about properties and they need to be geocoded. You just can't use the zip code for this. So, and that can be a big issue. So for the weather data, so we have a hurricane. I used basically two models to predict it. One's a prediction model, and that's occurring about 24 hours or 36 hours. A hurricane's going to make inland, and I need to have a number that I give up to my executives, like how much do you think that this hurricane's going to cost us? And so, yeah, during that time, it can be up to 20 to 18 hours beforehand that we try to predict for that. And then the other one's post hoc. After the hurricane's gone, I bring in some real-time data and try to figure out, okay, so what was the actual loss there? So with the prediction model, we're using a weather model called the NAM. And so let me show you this right here. So this is on windy. So I got a lot of pretty pictures in my presentation. So come here, and I don't know if people are into weather. So if you want to forecast, what's going to typically happen, you go on local news, they're going to use two weather models to give you the prediction. So it's going to be the GFS, and then this second one's called the Euro model. And you can kind of see, you predict it out, and you can see there's some variance between the different models. And for us, you probably just want to know temperature, maybe precipitation. Wind's very important for us, and then for each model, there are hundreds of different elements you can have at multiple layers in the atmosphere. And I'm going to show you 10 different ones for the predictive hurricane, and I show you a few more for the post hoc one. So the GFS and the Euro, and then I focus on the NAM for a couple. It actually has it's just a little bit easier to use. We'll say that for data engineering. And then one internally that we're using is the HER. You can see the resolution is a lot smaller comparatively to the GFS. So if you want to look at the GFS, this is a great little app that shows you what the GFS is predicting with the wind. If I go back in time, let's say last year we had Hurricane Helene, and so we can. So you can see Helene making landfall like this. So it gives you a lot of data that you can actually use. So this is this wind. So it's giving you two different vectors that you can both get the magnitude of the wind and also the direction. And then, so what I do is about 24 hours before landfall, I basically figure out where the landfall is going to be. I use these shape files from the National Hurricane Center and try to figure out at what point and about where it's going to make landfall at. And then I go in and I gather a bunch of data from these weather models. And so this is an example of the HER model. So you can actually see this is their predictive model of hailing. So you can see that coming in. So these are wind gusts, and this is what they're predicting what's going to happen about 24 hours. So this gives you a lot of data. So the HER model here is at a resolution of 3 kilometers, which is pretty fine. The NAM is the one that I use actually at a, it's at a 12 kilometer resolution, so it's not as fine grained. But you can do a lot of things with that. So you have this over time, and you have about, it's 48 hours worth of predictive time frame, and that you can compress this data. So what I do is I take the max of a given element, so it'd be wind gusts, precipitation, etc. I take the mean, I take the standard deviation, and I also do the min. So they give me kind of 4 different metrics per element. So what I do there is I pull this in and I attach it. So this is kind of gives you an example of what the data looks like. So to hailing. So we can see, so this is the precipitation. These are the wind vectors. So the U is eastward direction, so it's going to give you, if it's going eastward, it's going to be positive. If it's going westward, it's negative. V is north and south. This is mean level sea pressure. You got a couple other ones. Wind gust. You have the wind, how it deals with different the terrain and whatnot. This is dealing with wind, an upward draft. And then we also have things like distance to landfall and distance to coast. And then on top of that, I didn't put it up there, we have our exposure data as well. So for each hurricane, for the predictive model, I had 50 different features that 50 different images that I put together. And then I do feature engineering, I use a PCA, I kind of compress the data down, if you will. And then from that, I train a neural network to figure out what the total loss is. I'm going to get that in a second. So that's it for the NAM. For the post hoc one, we use a couple other ones. So here, so we can do flooding events. So this is called the average recurrence interval. It basically tells you how much you have, how much rain you have in terms of flooding.
You're on 2020.
Yeah, I did. Right there. So you can kind of see. So I don't know if you remember hailing last year. There's a lot of flooding up in North Carolina near Ashland. And so we were able to use this model to figure out, hey, how much flood exposure do we have in that area? And then what's our total loss going to be based on that? And we were pretty accurate based on just this data. So other things you can do is rainfall. So you can do the rainfall. And then we do other catastrophe modeling besides hurricanes, and other things that are helpful is hail. Hail not so much on a hurricane, so there's not a lot of hail there, but that's very helpful for other stuff. Tornadic rotation is called the azimuthal, like how much you have rotation for a given potential tornado. So it doesn't mean if you have high rotation here that there is a tornado. You need to do, after the fact, somebody on the ground needs to verify that there was, but it does give you an idea of potential tornadic activity. So this actually happened in April of this year. So this is in the morning. So this is, we got, so I live in Milford here, and you can kind of see at this time we lost power for 20 hours, right? So you actually can see on the map this azimuthal, this rotation, and knocked out our power. So these are the elements that we use for the NAM, so just in case all 10, so I'm not going to read through them. These are the 10 that you use there. And honestly, what I did for these, just changed from extend to extend. I sat with my son, who was 6 at the time, and we just looked at 500 images and tried to figure out which ones were most correlated with that. So next year, I probably need to do something a little more scientific, right? So, but that's kind of what we did. So it actually worked really good. So with the prediction model, we can get mean absolute error about 700,000. The average hurricane loss is about 4.5 million for us. So it's pretty good. So this is, I'm pretty happy where it's at. I could use. It's actually changing. We have geodes. I'm trying to duplicate this. Yeah, just duplicate there. Maybe just let's try this. There's one. Oh, there it is. Is it just tucked in that? Okay. So it just keeps changing text. Sorry about that. So for the dam modeling, this prediction model, we use about 30, I think it's 34 storms, and we have different targets. We have hazard, essentially flood, and incurred. So incurred is both the hazard and the flood. So basically wind would be considered hazard, so there might be some other stuff involved with that. Like I mentioned, so we have 50 different features per hurricane. So we do a PCA, which actually reduces the data. I did 3 principal components. I've experimented with other dimensional reduction techniques. PCA works the best for this. I'm hoping to try some more out and see if I can get better results with there. And then during the training process, I'd use data augmentation. You just take the images, you kind of spin them around, change them a little bit. And then with minority oversampling. So AI, so let me get into how exactly I do the predictions. So if for those of you who have not dealt with deep learning, 2 books I recommend are these up here. So I'll highly recommend, especially if you just don't know anything about this. First one has a really good section on machine learning. And so what neural networks are is you take an image or something and you re-represent it through layers of successive layers of representation. So for example, we have a dog, and we put it through the neural network and it spits out. So you have an image of a dog, put it through neural network, and it spits out a dog versus a cat in this case. So in this case, we have a 4, and then we kind of change it versus these successive layers. And it's going to then, at the very end, it's going to spit out a value from, you have 10 different possible features, and it's going to give you a predictive value for those. So specifically with a convolutional neural network, if you have an image is just a number. It's just basically a matrix of numbers. So a typical image has 3 channels, RGB, red, green, and blue, and you just have numbers. And so what you can do with these numbers is you can manipulate them, and we're going to manipulate them through the neural network. So 2 operations I want to show you that are very common are a convolution. So you're just basically taking the image, and then you're multiplying by a filter or a parameter, or it's called a kernel or a filter, and then you just, from there, you just multiply. You're doing matrix multiplication, so you go from one matrix to a smaller, different matrix. So that's the first operation. The other operation is max pooling. So pretty simple, you just kind of look on a given area and you find the max amount, max value. So with these 2 operations, we can create a neural network. So the most famous one that anytime you open up a book on deep learning is the VG16. The reason why it's called 16 is because there's 13 layers of convolution, and then you have 3 more fully connected. I'm going to skip fully connected just for time's sake. But as we went back here, we have the 2 main operations, convolution and max pooling. And what's happening here, and I'm actually going to show you how this works explicitly in a second, is you're going to take the image and then you're going to multiply it by that kernel, that filter, and then you're going to get 64 different images based on that kernel. And so, and you kind of keep doing that down all the way to, at the very end here, in this model, it has 1,000 different possibilities, and you'll spit out a percentage for each one. So let me make that more explicit. So here is the VG16, and I'm on Hugging Face if you want to see some of my stuff, so you can see this, obviously, all open source stuff. we put an image here, and then the model, basically the VG16, does a bunch of multiplication and spits out these values at the end. So there's actually 1,000 possibilities. I just did 500. So you can see right here, golden retriever gives a 41% chance of it being a golden retriever, 30% chance of being a Labrador retriever. Now, if you know anything about dogs, that is not a golden retriever, though it looks like it. So this isn't a very good model, but it's very simple to use. But what we can do now is we actually can see the image go through that neural network, and that's what this is right here. Let me see if I can make this a little bit bigger. It's a little hard to see. Oops, that made it way too big. Does anybody know what they said? Right. Anybody know how to actually get this out?
You're trying to press
Yeah, I don't know what it just happened. It's just, yeah, so it's like, yeah, no, it's not doing that. It's like completely froze. Yeah, it's okay. Oh, there it is. Okay. Okay, we'll pretend that didn't happen. I apologize. Sorry. Okay. I think we're good right here. So what's happening here is on the first, we have input of a input of an image, and then that first layer of convolution gets right here. So you can see the model multiply and actually augment the image as you go down. So these are the first two layers of convolution, and this is the max pooling, and then it just keeps going down. So what's happening is the model is doing a bunch of multiplication and addition, and you're going all the way down, and it's going to spit out a final answer based on that. So So what I do at the very end, and this is called transfer learning, is instead of spitting out 10,000 or 1,000 different possibilities of different categories, I just change that to one number. It's going to spit out one number. The number that I'm going to spit out is the total incurred. So you're taking this as a classification or recognition model, and we're turning it into a regressor. I'm good. I think I get it. So, and then not only do I do it with one model, I do it with two different models, and then I put them together in a neural network, and then I spit out the final answers. So some of the best models I found for this are the GhostNet, EfficientNet, etc. So these are our convolution neural networks, and I do some vision transformers as well, and be able to take all those weather image data, and then put it through the neural network and spit out an answer. Like I said, it's pretty accurate for what I needed to do. Okay, the second part, a little bit easier, and this is probably more like something you guys can actually try on your own, is unstructured data. So when a hurricane comes in, it gives you a bunch of advisories. And you can actually, it's just free-form text. Of course, it's not. So with these, you have different free-form text. And what I do is I use an LLM to extract data from this. So the prompt that I use is this. So rate the following items from 1 to 10 and place in the table with each rate as a column and two additional columns for storm and number. So I ask it to rate it based on overall severity, wind severity, etc. So this is the prompt. and then I can put it here, and then I can go in and just grab this data right here, and this will actually create a table for me that I can then use with a machine learning algorithm. So right here, it spits out a table. Now, there's obviously some caveats. You probably don't want to do that one time, multiple ones. You want to use different models. So if you look at two other models, LM Marina, I'll just pick two right here. We'll do, I'm just doing these because they're fast more than anything. 5. So same thing. You can kind of compare the different ones. So they're going to spit out different answers for each one. And sometimes if you rerun it, they're going to get a different answer. So this year, I only ran each model one time and got the answer. Next year, I'm going to do it 3 times and take a mean of each one. So you can kind of come here, and then you can kind of see, so we give me the table. So, you can see the table. So kind of looking at that one. So this one, so 9889 at the last one. This one has the 978. And so what I did about, I don't know, 35 different models. And what's nice about this data, it's open source, so you can use it on any sort of LLM. So there's no really requirements. Nobody can get that mad at you for using that. So this is kind of what it looks like. So I did GPT-4, Turbo. So you can kind of see. So I did some of the smaller llamas. Another thing I tried is I summarized it beforehand and put it in, and that didn't work as well. And then what I found to be the best is if you take all the hurricanes and all the advisories and put them into to the LLM, and that for me that was like 300,000 tokens. And so at that time, when I did this in the spring, there really wasn't that many LLMs that would take more than 1 million. So Google that I had access to was the only one that did that. And that's the best one that I got. So it's a Gemini, at the time it was Gemini 2.5, I think it was experimental. That ended up being my best model for this. I tried different ones, even tried some local ones. Didn't work that great, but. And then what you do with that is then you attach our exposure data and then run it through machine learning models and be able to get some pretty good results. Now, not as good as the predictive model. So the predictive model I said about 700,000 for the mean absolute error. This is closer to 1.5 million or 1 million, so it's not as good, but still good enough for my purposes, at least for an experimentation phase at this point. So I do use both first and 3 principal components, talking about the data reduction or the dimensional reduction with that. So some of the models I use, which I'm not really going to talk about, so random forest extra trees, GBoost, CatBoost, and NGBoost. Those are the best results I got from that. So in summary, the first part, for computer vision, we took structured images. We joined it with exposure data, did some feature engineering, which was the principal components, and then spit out a computer vision model, so using transfer learning to figure out how much loss was. And then for the LM data extraction, use unstructured text, use the LM to extract the features, join with exposure data, and then put that with a machine learning model. So some stuff I've tried, some extensions. I've tried cat losses. I'm almost done, so I don't need to ask questions. Just like so cat losses in general. So anytime we get a new catastrophe, I run models a little bit different, so add stuff like hail and convective storms in that. I tried that with the LLMs, didn't do a great job. I just finished a good round of training with being able to mask hurricane losses. So I'm able to figure out where in the general vicinity our loss is going to occur based on your exposure. So that gives you a map and then the general areas of that. We tried with wildfires. We're making progress with wildfires. Wildfires are very very random stuff will happen. So for example, in the Palisade and Eden fires, you'll have a house, 2 different houses. One, the Santa Ana winds might have just blown open their window and some embers got in and burned the house down, and the other 3 houses down the street are just fine, right? So getting closer with wildfires, but still need to do work on that. And then the last thing, been experimenting a little bit with agentic data extraction. Like I said, what I've found to be the best is take all the data, just throw it into an LLM, and get the feature extraction. So, yeah, any questions?